opportunity to come here and talk. We talked about some of the work we've been doing about studying the circumgalactic medium of dwarf galaxies in simulations. It's work I'm doing with my advisor Chris Churchill, along with my collaborators Sebastian Gomez, Elizabeth Klimek, UC-HiPACC, and Angela. Okay. So we've had a pretty good introduction to what is the CGM, so I'm not going to spend a lot of time here. Key points, it's just a diffuse gas reservoir surrounding a galaxy, can extend out to a few hundred kiloparsecs. And the key point really is that it's typically observed through absorption line studies like in spectral quasars. So what goes into that? There are some difficulties with this in that you are only getting a 1D test, and it can be kind of hard to interpret what the absorption lines tell you. If you want to get thermal properties of the gas, densities of the gas, a very common technique is to use void profile fitting. This has some inherent assumptions built into it. Mostly that the absorbers that you are seeing are cloud-like, meaning that they have constant density, constant temperature, and are spatially coherent. This also assumes that somewhere along your line of sight, in your spectra, a line of sight velocity corresponds to a distinct physical location. And when you do a void profile fit, you get something like what we have at the bottom here, where it's a void profile fit to a carbon-4 line. And you'll determine that there are probably 3 components. So you're intersecting 3 absorbers, and for each one of these you get a density and a temperature out of it. So what I want to look at is really how valid are these assumptions? Where are we seeing these pan out? And to do this, I'm looking at simulations. So I'm using cosmological zoom-in simulations using ARC, as run by Sebastian Gomez. And I'm looking at isolated dwarf galaxies. We have a virial mass of 3 times 10 to the 10 at redshift 0. And our technique is the basic synthetic spectral technique. We run lines of sight through the CGM of these galaxies. And based on the properties of the gas along the line of sight and the kinematics and any instrumental effects we wish to include, we can generate synthetic spectra. And across the bottom here I have 4 examples for hydrogen, magnesium 2, carbon 4, and oxygen 6, 4 very commonly observed ions. And what I want to do is then fit void profiles to the spectra, determine what would be the deduced physical properties of the gas, and then compare it to the actual physical properties of the gas in the simulations and see how they line up. And this work I'm describing now is going to be put out in a paper, hopefully by the end of this week. So keep an eye out for that. And I'm only going to be looking at results for a single line of sight, just for initial analysis. And in this busy plot, the x-axis for all these plots is distance along the line of sight. So from where the line of sight enters the simulation to where it exits. We have each column is a different ion, and we have number density, temperature, metallicity, line of sight velocity, and column density for these gas cells. And these are the inherent properties in the simulation. Where you see them highlighted, that's where the cells that contribute significantly to the absorption profiles are located. So you can see that for hydrogen, all these cells in the simulation that contribute to the absorption profile reside at this peaking density, this dip in temperature, and they're all at this point in space along the line of sight. Magnesium 2 is something similar. Carbon 4 is a bit more spread out, and oxygen 6 is significantly spread out. Okay, look at these a little bit more in depth. Okay, so remind we have a spectra across the top, and now instead of a long distance along the line of sight, these plots, x-axis is line of sight velocity, so this is what you would observe. We have temperature and number density. And we see that for hydrogen and magnesium 2, the cells that contribute significantly to the absorption are pretty much uniform in temperature and in density. So kind of what you would expect for the void profile assumption. With a carbon 4, you're about half a deck spread in temperature and about 2 decks spread in density. And similar for the oxygen-6. So the absorbers that you're seeing for the carbon-4 and oxygen-6 are not constant density, constant temperature structures. We can also look at where these things reside along the line of sight. So it's the distance along the line of sight compared to line of sight velocity. The hydrogen and magnesium are nicely spatially coherent. The carbon-4 and oxygen-6, not so at all. In fact, if you were to pick a certain line of sight velocity, you could be intersecting upwards of 5 or 6 different places in the CGM. So, and you wouldn't be able to tell this from the observations because all these overlap with the same line of sight velocity. So this helps to say that the magnesium 2 and the hydrogen, the lower ionization ions, tend to be cloud-like. They have the constant density, constant temperature, spatially coherent. While the higher ionization ions, such as carbon-4 and oxygen-6, are not. So the lower ionization ions seem to be fulfilling our assumptions about what profile fitting, while the higher ones not as much. Another note we can look at is that if we look at where the hydrogen and magnesium-2 reside along the line of sight in simulation, there are some cells, these same cells also give rise to some carbon-4 absorption, but not the oxygen-6. Our oxygen-6 and our H1 absorption are completely not affiliated with each other.
Is this a funny example, or are all your halos pretty coherent in line of sight velocities, no matter where the gas is located?
This is just for a single line of sight. So we haven't yet done the full analysis through all of our halos and all of our lines of sight yet. Yeah. So the next part of what I want to talk about is what's going to be detailed in a second paper that should be coming out in a month or so. I want to look at how changing the stellar feedback recipes used in these simulations alters the observed circumgalactic medium of these galaxies. So I'm looking at low redshift, less than 0.1, and we have 3 feedback descriptions: supernova only, a weak radiation feedback, and strong radiation feedback. And the only difference between these is that the radiation feedbacks include radiation pressure and photoheating, and the strength of these is just the strength. The only difference is the strength of the photoheating. So the radiation pressure stays the same between the all 1 and the all 8 simulations. And the effect of these different feedback descriptions is detailed in Trujillo Gomez et al. 2013, and it has drastic effects on the properties of the galaxies itself, such as the star formation rate. The supernova galaxy, the supernova only feedback is very quiet, very low star formation rate, while as you increase the radiation feedback, you get much burstier feedback, to the point where all 8 within our redshift range undergoes 3 major bursts in star formation. So we're going to look at how this alters the CGMs. We ran 1,000 lines of sight for each snapshot and looked at the global average properties of these galaxies. The first thing we looked at is the equivalent width versus impact parameter. So we have the strength of the equivalent width versus our impact parameter. We go up to 1.5 virial radii. We have our hydrogen, magnesium 2, carbon 4, and oxygen 6, comparing the different feedback mechanisms, and kind of a bit of reaction. There doesn't seem much of a difference. These feedback mechanisms, which cause strong differences in the galaxy itself, do not seem to be having much of a different effect on the CGM itself. We also looked at covering fraction, which is a way of thinking like what is the probability of finding an absorber at a given impact parameter. And you can see similarly, for most of the ions, there's not much of a difference between the different feedback mechanisms. The one that stands up strongly is oxygen 6. For supernova only, you have a very high covering fraction at the inner regions. As you increase the amount of radiation feedback, your covering fraction drops significantly in oxygen 6. So if we want to compare, find a way to get a handle to compare these observations, just give a crank of which one of these best produces a real-life CGM. Oxygen 6 may be our best bet. However, if we look back at the equivalent width of these oxygen 6 absorbers are at or below detection limits for most surveys. So the oxygen 6 halo in these dwarf galaxies are sensitive to the feedback restrictions, but aren't really observable. Which is a bit of a shame. So in summary, our low ionization ions tend to arise in cloud-like structures with the constant density, uniform temperature, spatial coherence. So void profile fitting is very appropriate for these. The higher ionization ions, not so much. So if you do choose to use the void profile fit on these, just have some caution in how you're interpreting your results. The H1 and O6 do not arise from the same locations from the same gas. And the global properties of the CGM around these dwarfs is relatively insensitive to the stellar feedback details, the possible exception of oxygen 6.
So, carbon-4 and oxygen-6,
Mm-hmm.
you say bit of caution, but it
Yes.
seems like it's, maybe worse than that. But one question I wanted to ask is, in a lot of studies, one fits, and I'm not super familiar with this, but my understanding is one fits a bunch of lines, including carbon-4 oxygen-6, with a single ionization model to try and get out some idea of what the cause might be. This may be somewhat sobering in that regard. Have you thought about what the implications would be for that kind of polarization modeling?
Well, the way we did these is that we had, you're right, normally a lot of people will tie all the ions together with one model and call it good. We separated these out, so we fit the low ionization with one model, the high ionization with a different model. And we picked a solution that had the lowest number of components. And it could be that if you allow you to get more components, you're going to do a better job fitting your results. And one thing we did note, if you're going for, I didn't get a chance to show this, but if you're looking for like column density, if between our different models, we determine the column density in 3 different ways. Do the void profile fitting, AOD column densities, and then just adding up the column density along the line of sight. And if you only want the total column density, not the column density of components, all 3 methods give just about the exact same answer. So in that regard, that still works out. As for other quantities, yeah.
All right, in the back.
Just to qualify that, if you're using a void profile, you're basically having to assume that the gas obeys a Maxwell-Boltzmann distribution, and that may not necessarily be the case when you have these high ions which are distributed over large volumes. That's all it's saying.
I should say, to answer just a little more Eric's question, if you try to do a photonization model that does H106, you find the same thing as bullet through. You can't, not surprisingly, you can't do that without ridiculous physical conditions.
Yeah.
So we don't try and do that.